Hi everyone, this is Carlos from the EMAC Science Support Team, and today we're going to be looking at TRICERATOPS. TRICERATOPS is a Bayesian vetting and validation tool for TESS exoplanet candidates. So we're going to hop right into it. This notebook that I'm showing y'all can be found right here. When you go to download, it takes you to this GitHub. You can look into their examples, and here is their Python notebook that they created for us, and it's super thorough. So they list 3 examples in this notebook. We're just going to look at the first one. So the first one, how to apply Triceratops on a star observed in a single test sector without follow-up data. First thing you're going to do, you will import all of the modules you'll need. A couple things to note, you're going to import TESS light curve from light curve, and you're going to, of course, import triceratops.triceratops.str. So again, first example. In this first example, we're going to be looking at the candidate WASP 156b. So as you guys can see here, this target was observed with a 2-minute cadence in sector 4. So the very first thing we're going to do is we're going to upload this data into our notebook. So we will set the ID, this ID right here. This is the tick ID for WASP 156b, sector 4, as mentioned up here. And we will just set target equal to our TR, that's the Triceratops, dot target ID is equal to ID, sectors is equal to sectors. So basically this is saying this is our target. Now looking at our target, this is what we have just uploaded. Now what we are going to do is we are going to use the dot plot field to look at our star field. And then we are going to also look at a table of all the stars that we see here. So this AP is equal to MP array. This is an array of our aperture, and we are just going to set that equal to AP pixels. And of course, sector 4 is still going to be sector 4, and this target.plot field will plot these star fields. As you can see, we have plenty of stars, with our main one being in the center. This is the one we want to focus on. And going down, you can see this table that includes all of the stars or targets of interest that we see in these images here. Now, next thing we want to do is we're going to use .calc depths to calculate the probability of any of these targets of interest having a transit depth of about 5,000 parts per million. So all we are going to do is, again, set aperture equal to our MP array of apertures, and using .calc depths, we are going to calculate which of the TOIs inside these images is able to produce a transit depth of 5,000 parts per million. So again, using target.stars will give us our table, and we see all of our targets of interest and their possible transit depths. As you can see, only one of them is even able to produce such a transit depth. And if you look here, this same ID corresponds to this ID. So still looking at WASP 156b. Awesome, we have narrowed it down. So far we are saying this transit depth is possible. Next thing we're going to do is we are going to use .calcprob to calculate the probability of this transit depth occurring with a bunch of different scenarios. So here we are going to read in the TOI 465 light curve data. So again, this target of interest 465 corresponds to target of interest 465. So still looking at WASP 156b. And using light curve, we are going to set time, flux, and flux error to the values inside this .csv file, and p_orb will be the orbital period of the TOI in days. We are also going to bin our data. Typically, it's not a good idea to bin your data when you're doing these kinds of calculations, but here the authors tell us that it doesn't make that big of a difference, so we're going to go with it. So now we have set our light curve equal to the TESS light curve, and we are going to use target dot calc probs to calculate the probability of all these scenarios. So this will take a little bit to run. No worries, it's doing a lot of math. No need to panic. As you can see here, it took about 3 minutes and 40 seconds. Not too bad. Now coming down, we want to find out what the false positive probability and the nearby false positive probability is. So using .probs and using .fpp and .nfpp inside .probs, we can calculate that super easily. So you just set your results equal to target.probs, and you're just going to have it print your FPP and NFPP. Here we go. FPP of 0.0053. Interesting. Okay, so looking at our results, here you can see the probability of all of these occurring given these scenarios. And for fun, we can use plot fits to plot all of these different scenarios. So what we're looking at here is real data and models being plotted over them. And here it tells you what scenarios you're looking at, which is super helpful. Now the big thing is we want to publish, right? So if you're going to quote the things you get from Triceratops, the authors insist that you run .calc probs a couple of times to make sure that your results are not showing any sensitivities to intrinsic scatter. So they ran it 20 times. They write this loop for us. And then coming down, we have this FPP equal to 0.0864, which is favorable, but not low enough to validate the planet. So that's Triceratops. There's a lot more to this, but we only wanted to go over the first example because it's more fun to figure things out for your own sometimes. So yeah, I hope you guys liked it. Please follow us on Twitter and like and subscribe to our YouTube channel. And yeah, peace.